In this video, we'll move into section 4.2, where we will discuss the variability of a data set. However, just before we jump in here, I want to go back. At the end of section 4.1, we had a little bit of discussion about what happens when the mean and median are not so close together. We saw several examples, and especially if you went through the book and the homework as well, a lot of examples where the mean and median are pretty close together. It's a pretty common occurrence. There are two different ways at looking at what is average, what is common, what is in the middle. So in a lot of different data sets, that value that we use to represent that middle, that common value, it's not too surprising that they're fairly close together. However, I did just want to point out that there are situations when they are far apart, and when they are, that's where we have some of those opportunities for misuses, opportunities to mislead, an opportunity for you possibly to, or someone in a situation to present one side of the case, where maybe the median is something that shows their agenda, that shows their side of the story a little bit better, or the mean, and there are situations where either one might be a little bit more helpful. So the point is that simply we should be interested in both values. May only see one or the other. Again, often they're close, but just something to ask. When we're looking at what else can we want to know, well, that would be one thing. If you're only getting one value, it certainly wouldn't hurt to have the other. And if they're not a similar value, to then start to think about why that might be the case and which one might be more appropriate in that situation. Okay, so mean and median, and we're not completely done with that. We'll still see those continue to come up. But now we start talking about the variability. This starts looking at more the spread of data. Looking at the first piece, the idea of the mean, the median, what's in the middle, what's common, that certainly tells us a lot. If you were going to give any kind of report on a data set, that average, that common value would probably be one of the first things you say. But we have to realize in any situation, if you're comparing two different items, just because they have the same average, they still may have very different data sets. And that difference may be the spread. Are the data values all closely packed in close together in very close proximity, or are they very spread out far apart? So thinking very quickly about test grades. If I told you two different classes both had an average test grade of 75, but one class, everybody is all right around that 75. A couple of people have a 76, 77, 78, but they also have those people who have a 74, 73, 72. But everybody in that class is right in that very close bubble. So they have an average test score of 75. But what about a different class where half the students scored a 100 and the other half scored a 50? That would also lead to a 75 average. So which class is better? Well, you may have a different opinion, and there could be different evidence that shows maybe class A was better because the class as a whole all had better results, but maybe other people might say class B is better because you have so many people who had a perfect 100. So, there are different ways to look at it, but just having that average value of 75 doesn't tell us enough. It gives us a good piece of information, but we'd love to have a secondary piece that tells us, again, that spread. Are those data values close together, or are they spread far apart? And that's not just something that we think about with test grades. If we think about, time spent, whether it's commuting, time spent on a homework assignment, same thing. Some people may finish that homework assignment very quickly. Others may take a very long time, and then people in the middle. But that that idea of variability, which we'll get to the standard deviation and the idea of variance. Those will be two of our big tools in just a moment. But that spread, if we have, again, the person spent a lot of time, spent 30 minutes, and the person who got through it quickly only spent 20 minutes, that's, fairly close together versus somebody finished the assignment in 5 minutes and somebody else took them over an hour. So again, the spread of data. If we look at a company and we want to look at how much they pay their employees, certainly the average amount, but again, the spread. Do we have a lot of high and low salaried employees? Is there kind of just a middle ground where everybody gets paid the same? If we're looking at production, if we're looking at maybe recovery from surgery, if we're looking at how long it takes us to recover from medication. Again, all these things that I'm mentioning, just lots and lots of examples of statistics. The average value certainly gives us a lot, but then having that next piece about the spread of the data. Okay, so that is a big introduction to the idea of what we mean about variability and where we're going. Now let's start to see some of the particulars. So how do we measure the variability? There's three different ways. We have first what we call the range. The second piece we call the variance. And the third tool that we will find is the standard deviation. This is the big one. Just like we've seen, mean and median in 4.1, the mean is going to come up a little bit more as we go along. In this section, the range is interesting, certainly is a very quick piece we'll see in a moment. If you go a lot further in statistics, have a second course, maybe specializing in a certain area, it's possible you may see the variance come up a little bit more, but for us, we are going to see the standard deviation quite a bit. So, the range, our first one, is very simply the highest data value minus the lowest. That's all there is to it. It is simply just trying to see then literally the range, just like, some of your other math classes, the idea of range in algebra, the y-axis, what is the lowest y value to what is the highest y. This is that same idea, but actually subtracting those two values. I'll put an equals here so we see that as a formula. And that again, just looking at that first test example I gave, if the lowest student on the test scored a 72 and the highest scoring student got a 78, the range is only a 6. There's only 6 data values, 6 points, I should say, from the lowest to the highest. But in the second example, where the lowest student got a 50 and the highest got a 100, the range is 50. A much, much bigger spread has a much, much bigger range. So that's all there is to it. And again, all the other examples, we get that same piece. So that certainly would be a nice, helpful piece, but still is very limited. This certainly, we keep mentioning the idea of an outlier. We'll eventually get to that formal definition. I believe it comes up in 4.3, we get that formal definition. But, still mentioning that idea of extreme highs, extreme lows. Well, again, think about that test score example. Let's go back to that first group that was everybody was a 75, a 77, a 72. Everybody was in that very close proximity with 75. But then one student gets a 12 on the test. Now all of a sudden that range becomes a huge number, and it's all just because of one student. So again, range is a good indicator, but an outlier can really throw it off. And we're certainly looking for just better overall ways. So before I formally define these two, and these go hand in hand together, before I define them, first we just have to talk about what we formally mean by a deviation. Specifically, we're talking about deviations from the mean. Well, we'll find out in a few moments that this idea of a mean is literally the geometric center of your data. So if we're going to talk about the spread, that will be a necessary piece we'll see in just a moment. So this idea of a deviation from the mean, that we've already seen some of our notation, our symbols, that x we use for a regular data value, and we could start putting in the subscripts, x sub 1 for the first data value, x sub 2, but just generic x for the data value. And we use x bar when we're talking about the sample mean. This idea of the deviation is literally just the subtraction of the two. So again, I know I'm saying a lot of quick examples. In just another minute or two, we'll start to actually do it together. But back to that first test example, if the average test score is a 75, that would go right here if that was your sample mean. So somebody who had a 77 on that test would have a deviation of 2. 77 minus 75 would be positive 2. Your deviation could be negative if someone had a 74 on the test. 74 minus 75, they would have a deviation of negative 1. The negative, this is important, everybody. You don't just do big value minus small. We're always doing data value minus the mean because the positive or negative tells us something. The positive giving us a clear indicator that data value is bigger than the mean, and a negative that the data value would be smaller than the mean. So we don't ignore that plus or minus. That is important. We bring all this up because this comes back to, again, what the mean really tells us. That idea of the numerical average, again, there's a lot of funny geometry that people don't really think of when you're thinking of numbers, but there's a geometry, and that mean is the real middle of that geometric set. And if we look at, there's that summation symbol again, the sum of all of these deviations, so that's every single data value. We line them up. They don't have to be in order for this, but just to make sure that we go through every single one. Every single data value minus the mean. Keep going, keep adding those, and remembering that some of these deviations could be negative or will be negative. Again, if we're getting the mean, what's in the middle, that means we'll have data values that are both bigger and smaller than the mean. So we'll get both positive and negative values, and the sum of all those deviations will add to 0. That again, that's that supporting that idea of the mean being truly the middle. You look at all those deviations, all the subtractions, how much bigger from the mean, how much bigger than average, how much smaller than average, and then add all those values together and you get 0. That puts you right in the middle. So, how does that help us? Well, now that we have this idea of a deviation, now we can actually talk about the standard deviation. Again, similar to the mean, two different pieces of notation. We're going to use S, and we're going to have, this is lowercase sigma. We already saw uppercase sigma. Now this is lowercase sigma. And again, it kind of looks like just a little O. Technically, though, you just have that little hook at the end. It's not just an O, that you've got that hook. And even how you make it, just a little bit, again, that's perfectly fine, but you technically start here and loop up and around. But the point of the two symbols, just like we saw with the mean, we need to be able to distinguish when we're looking at only a sample versus when we are talking about the entirety of the population. So, kind of like, X and X bar, we used a regular letter for when we're looking at sample, and then we use mu. So here we're looking at sample. Same thing if you ever looked at population, that would be how you define a deviation from the mean. Just capital X to indicate a data value from the population, and there's that Greek letter mu. So mu for population, X bar for sample. Well, in standard deviation, the S is the sample standard deviation, and the sigma is the population standard deviation. There are formulas for both. Our book at this point only gives us the formula for the sample. So I'll point that out right now, and I'll relate it back to this in just a moment. So our formula, S equals, we get the summation of X minus X bar quantity squared. All of that divided by n minus 1, all of that under the square root symbol. That is what we are looking at. This formula, the book brings up the variance formula first. I'll come out and point that out in just a second, but they're very much connected. So there's our formula. What is going on here? I mean, first thing just to point out, we have that summation symbol again, that idea of sum of. I kind of quickly mentioned it here, and I will again show you with a specific example in a moment. But there's that summation. But what is this actually doing? The point of this, what is actually happening here, is that the standard deviation is, in a sense, the average deviation from the mean. So now we've thrown that word average around a lot. The mean is already the average data value, but now the standard deviation is the average deviation from the mean. So when we keep looking like at those test values, how far is each one from the mean? Well, you're 1 point away, you're 2 points away. Or if you're looking at salaries and you're 1,000 more than average, you're 10,000 more than average, you're 5,000 less than average. But all those, the idea of the standard deviation is trying to find the average of all those deviations. But here, the reason we end up squaring this value is because we pointed out, if we just look at the deviations, we get positives and negatives. Positives, again, for above average, above, greater than. I don't always want to make above average sound like a good thing, right? We could certainly situations where, if you're running a race, if you're above average, you're actually considered slow. You'd want to have times below. But just that idea of, again, just positive, just being more than the average, and a negative deviation being lower than the average. But again, having the positives and negatives, adding them together gives us 0. But if we square all of those values, now all of those values have become positive. There's a little extra reason why we divide by n-1 instead of n, but all the deviations squared, divided by how many you have, and then take the square root. It's like these undo each other. So again, I'm not trying to get too deep into the whole, why that formula is what it is, but just to give you a little more understanding of where it comes from. So now we'll practice using it. The only difference for population, I'll just point it out quickly. The square root is still on everything, just you only have n instead of n-1. So if you ever use like a calculator feature, or eventually we'll see this on Excel, you'll see that they always mention both standard deviations, and they're very subtly different values. And it's just because in the sample, dividing by n-1, versus in the population, only dividing by n. Okay, last bit, and we could finally start to get some practice here. So how does the variance tie into all of this? The variance and the standard deviation go hand in hand. The variance is simply the standard deviation squared. That's all there is to it. Like I said, more higher level, like a second or third level course in statistics, there are some formulas that use variance, but for our purposes, that's all we ever need to know. If you know the standard deviation is 5, well, then the variance is 25. If you know the standard deviation is, 15, well, then the variance is 225. It's just always squared. Or vice versa. If you know the variance is 100, well, then you would take the square root and the standard deviation is 10. That's all we need to know as far as going back and forth. And now, again, we'll really focus on the standard deviation. So let's start off with a couple of examples. Let's say we want to look at, we have a bunch of people are having a broad jump competition. So we have a bunch of students and they all take a broad jump, and these are their measurements. These are their jumps, and these were recorded in inches. So we've got someone who jumped 32 inches, 21, 16, 44, 51, 34, 30, 22, 24, and 24. Let's find the standard deviation. Oh, and let me be very clear here. Again, we're only computing sample, but I always want, and the book does this too, they always make it clear we're always looking at a sample. So we have a sample of students who competed in this broad jump, and that their measurements are recorded in inches. Let's find the standard deviation. Well, the first thing to realize is that if we're going to find the standard deviation, there's our formula. Even if we're not asked for it, we actually have to find the mean first. So the mean, just to quickly remind us, the summation of x divided by n. So these are all of my data values. And n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 students. So I'm just going to quickly type these in. Again, the little things, like I said, just showing me a little work, little formula. If you want, actually, this is a very good one for me to do this. Let me make a whole formal column because I really want to show that off when we get to this formula. So I'm going to start off x. And, I'll give you a quick reminder of the median while we're here. So I'll also take advantage and put these in order. So I'll go 16. Then next we've got 21, 22, 24, 24. So there are all my x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got all my x's. Now I sum these up. Normally I wish I had just a tiny bit more room. I put my sum right underneath it, but I'll just put that on the side. Sum x, and when I add all those values, and I just take a quick peek, make sure I didn't have any goofs. Looks good. I get 298. There are 10 total students here, so we end up getting 29.8 inches is our average jump from these students. Okay, and little things, just thinking about units. Again, if these were salaries, thousands of dollars per year, well then this would be 29.8 thousands of dollars per year. The units, this is in inches here because all these were in inches here. If this was a time, how long it takes for you to get to work, and these were in minutes, well then that's in minutes. Again, not to forget, the units are important as we go through all of this. It's really easy to just, now that we're getting into the numerical component of the class, to just think, okay, I've got the number right. Units are a part of your answer. So something like a test grade, well, that doesn't have units, but for something that does, like this example or many of the others we've seen, be sure to put that in your answer. Okay, so there's the mean. Just a quick reminder, let's just get the median, just as, again, a quick reminder. 10 data values. If you do that n plus 1 divided by 2 formula, you would have 11 divided by 2 is 5.5. So you'd be looking at the average of the 5th and 6th values, 1, 2, 3, 4, 5, and 6. So you're looking at those two, 1, 2, 3, 4, 5, and 6 the other way. So if you did the median, the combination, the average of those two, you'd get the median is 27 inches. Again, this is where we had, I hate when people try and memorize this as even and odd cases. I'd rather you just have a way, and whether you're using this and know how to handle the decimal. The decimal always leads to the 2. You have to get the middle 2 values, or that you're crossing off, just working your way to the middle. Outermost, second, third, fourth, and then there you don't come to one middle, you come to 2 middle values. So either way, quick reminder, and then average those, you get a 27, 27 inches, 29.8. Again, fairly close. What is really close? What is spread apart? That's a little relative, but definitely those are in a close proximity. Okay. But all of that Now we really get back to the heart. We're finding the standard deviation. So there is my x. I've got x bar. Now, I mean, some people can still do a lot on their calculators, but now is when you're starting to get to almost too much. So slowly, what we're going to do is build to this formula. So in this formula, we have the summation of x. Once we had that column, we added it together. So if I want to do this summation, I need to make this column. So how do I get to x minus x bar squared? First, I do x minus x bar. Then I will square the value. After I make this column, this is what I will add. And now how people proceed through this is just a little bit of preference. But again, you needed the mean, which we know is 29.8. So now I will literally, one at a time, and I think you're going to see very quickly, this is can be a very tedious, time-consuming process. Want to be very clear. I expect some work. If all I see is a value, an answer, and even if it's correct, you're not going to get full credit on an exam. I expect to see some work. Not that you could just type into Google, find the standard deviation, and that it tells you the correct answer. So make sure you get some practice with this. So some people make this whole column, then they come here and make this whole column. Others just go all the way across. I'll show you both. For the people who go right across, they take advantage of the answer feature that all calculators have. That if I go 16 minus the 29.8, enter, and that goes right here. But some people don't mind skipping this because they could go right on their calculator. I've got a square button, and it automatically knows square what? Square my previous answer. So even if this was a little bit of a messier answer, instead of making too much of a mess on your paper, just 2 quick calculator operations, and that's the value that goes here. Here is the regular deviation we were talking about, but then we square that deviation. Here the negative was important, but whenever you square a value, positive or negative, it always comes out positive. So there's the deviation and then squared. So again, a lot of people like that as a 1-2. Even on my other calculator, same thing. If I go to the next one, 21 minus 29.8, enter. Negative 8.8 goes here, but then I can immediately just hit square. Same thing. The calculator knows, so I'll show you this in just 1 second. If you do negative 8.8 squared, notice the calculator still says negative. The calculator does what you tell it. It doesn't know what you want. And in this situation, the calculator sees the squared is just on the 8.8 with the negative out in front. It's literally this little difference. Let me jot it in my notes on the side here. The difference, it doesn't matter the value, the difference between negative 3 squared versus the quantity negative 3 squared. This is positive 9, and that's what's happening in this situation here. You're squaring, this value is in parentheses, so that negative would be a part of what you're squaring, so everything will be positive in this column. But again, a lot of people, if they don't use the answer key, it's very common they just type that, hit squared. They don't put parentheses in their calculator, so then they end up getting a negative answer. They get negatives here, and all their computations get very goofed. So another quick reason why I like when people show me all of the work that I'm showing you, and the reason is if something goes wrong. If I see your standard deviation is wrong, I could pretty much go back and find, is it just one quick computation mistake? You know, as we're doing this, you'll see we only got 2 of these done. I still have several more, but as we're doing this, it's really easy to just quickly, as you're copying a lot of numbers, accidentally forget a decimal, put something in. You know, as we get to the second part, this isn't terrible. I wanted a decimal here, but I didn't want it to be too crazy. But especially as you square, you know, these could be huge. keep a lot of spaces. Keep plenty of decimal spots. Don't round off now. Save the rounding for the very end. So if you get 4 decimals, copy 4 decimals. There's nothing wrong with that. At the end, round your answer. Don't round at the beginning. Speaking of that, going back to the mean, don't round that off to 30. I mean, that's a good answer. There's no reason to round that off. That's going to throw even more computations off. So make sure in the beginning, if we have to round off, if this decimal didn't cut off, well, then we want at least a few decimal places to minimize our error. But especially if we get something like this where we have a decimal, but it ends in a nice spot, we definitely want to keep that full decimal. Okay, so I've said a lot of advice. Now I need to start typing so we can get all these values. Just like I said, go through. And I don't mind if you go a little slower than me. That's certainly okay. You don't want to go too slowly. I mean, especially if we were in person, I would talk about not running out of time on an exam. And this, if you're not familiar with your calculator, can definitely be a spot. Here's the same data value, so I'll take advantage. I know I did my computation correct, so those will work out the same way. And now my value is bigger than mean, so I'll start getting some positives. But just again, to get some practice with your calculator so that it wouldn't come up on the exam, you're lucky enough to be doing this in an online environment with take-home exams. But still, it's good to have some practice. You don't want to be using your calculator for the first time on a test. Okay, just a few more. And last one. And you can't control the deviations. Our value is just a couple of points away. Are they further away? This is almost 14 below, a little more than 21 above. Now when you start squaring, big numbers, sometimes big decimals, you can't control that. You just got to take it depending on how the problem, what the values happen to be. So this is the important column. This is what we need to finish this formula. But I just want to come back here very quickly and point out what I was saying up here. Now, the tiny little bit, if you have to round off for your mean, we might have a deviation sum that is slightly off from 0, kind of like we pointed out when we add the relative frequency column in a frequency table. If you make the relative frequency column, that adds to 1 or something really, really close to it if things have to be rounded off, like 0.999 or like 1.01, 1.001. So similar here. But this one, because we didn't have to round off, look what happens. Keeping track of my signs, so I could write plus a negative 8.8, but just to make this a little quicker, I'll just go right to a negative. And honestly, folks, again, I put these data values in order so I could give you a super fast reminder of the median, but then I also wanted them in order just so I knew I was going to add this column, and I wanted to have all these negatives together just so it would be a little bit faster. But just to point out, if you never put these in order, that wouldn't matter. You'd end up with all the same values here. They're all positive. They'd be in a different order, but when you add them, you'd end up with the same total at the end. So let me just continue this part. Zero. As we said, that's the whole idea of the mean, getting you it's exactly in the middle. It doesn't mean that you have, this is, kind of a lucky case where 5 values below mean, 5 values above. That doesn't always have to happen. I mean, even looking at the ones below, you have a couple of these that are above that are just a tiny bit above, but then these that are a lot above. Then you have these that are all kind of a lot below, but the mean all lines up at the exact middle. So everything that's above or below, you add all this together. How far away in total are they from the middle? They are 0 away from the middle. So you don't have to do that. I point that out. Some people, like I was saying before, I did this value, then immediately squared. Some people just get this value, then get this one, then get this one, then get this one. They get all of this, then they just start squaring. In their calculator, negative 13.8 squared, or they don't even bother with the negative because they know it'll end up being positive. But in any way, whichever you prefer, this is the goal. Some people like to take a quick moment here, especially with the take-home exam. Make sure this adds up to 0. Make sure there isn't any silly little mistake that crept up, either just because you copied something wrong, or again, how easy it is when you're typing in a lot to accidentally miss the decimal point, to accidentally you go to do 16 minus 29.8 and accidentally miss the 9 and put 2.8. So again, a lot of computation means a lot of possibilities for little mistakes. So some people like this as a little bit of a checkpoint, but this is ultimately what I needed. The summation of x minus x bar squared is the sum of this whole column. So again, careful, tedious as you put all this in. And again, I really like, not everybody has the view screen. Most people do, again, even with this calculator. This one, if I type in a bunch, you go off the screen just quickly. And now you see I'm already going off the screen, so maybe just to be a little more careful as you're entering. But if you happen to have this calculator, just again, take that quick moment. Look to make sure the values are all there. No little typos as you entered them. Didn't forget a decimal point. Just these tiny little extra things can really save you sometimes some tiny little mistakes, sometimes some very, very frustrating mistakes. So finally, get that 1069.6. This formula, we're finally finishing this. That looked like such an ugly formula, but now that we've done, and we did a lot of work to get here, big square root, this value goes in for all of this. Okay, you did all the work. The summation of all of these values squared, that's why we did all the values squared to then add them, so that we've had that divided by n minus 1. Well, n was 10, so n minus 1 is 9. And now, calculator, square root 0.6 divided by 9. I mean, you could do 2 steps. This divided by 9, answer, then take the square root. A lot of people forget the square root, everybody. You forget the square root, you have the variance. But by taking the square root, you get the standard deviation. Now we finally round off. Finally, our final answer, and we get 10.9 inches. How far should you round? This is where, again, not too fussy. If you rounded to 11 inches, I'd be okay with that. But with all these decimals, it makes, it's good practice. A couple of decimals. If you went to the second decimal, the third, just round appropriately. And that's where we'll have some subtle differences, but that is a good answer. How do we use the standard deviation? Now that we have it, we've done a lot of explanation on what the standard deviation tells us, trying to get that. But I have to be honest, this is still very difficult for a lot of students, trying to get the grasp on how this information helps us. So I want to come back. Some people start to they start to understand it's the idea of spread. So in a simple direct comparison, this group of students had a standard deviation of 10.9 inches. If a different group of students had a standard deviation of 2 inches, well, just the smaller standard deviation means the values are closer together. So a lot of students can get that part. They could start to see that comparison. And again, we'll still get some more practice doing that as well. But I still want to come back after we do another full example and talking about how when we are presented the mean and standard deviation together, how we can use those together to talk about the entirety of the data set. But let's get another example. Let's look at this next one. Let's look at a little workplace example. We have a sample of 6 customer service representatives. And we are looking at how long they spent on their last service call. And we'll record that in minutes. So we had one rep, they were done in 15 minutes. Another one took 37 minutes. Another one took 71 minutes. Another one took 9 minutes. And we have 2 more. We have 20 minutes and 25 minutes. Let's find the standard deviation. The standard deviation for time spent on the last service call. So, like we just saw, first things first, we need the mean. Wasn't asked for it, but if I'm going to use this formula, well, part of this formula is x bar, so we got to start with x bar. So, sum x divided by n. Well, this time there's 6 customer service reps. I mean, tiny little things. Just to notice here, I told you it was a sample of students. We had to see how many data values there were to see there were 10. Here, I'm literally telling you there's 6. The book does things like that too, just to realize those tiny little differences. The sum x part. We get 177. That's all I need, everybody. Like I said, you could make the whole column. You could do more. You could show the formula, then do this. You could just show me this. But just to indicate, you're not just using some other tool, that you're using the formula. And when we actually do that, oh, actually, you know what? I'm sorry. Let's make this, I didn't want this to be so clean. 29.5, that was a little too lucky. So let's just make this last one 24 minutes. That'll make that 176 as the total. So now we get 29.3 forever. How far should you take this? Well, again, if you're just looking for the mean, not too big of a deal. But since we know we're going to do more with this, the better, the further we take this, the better. So if you take it to the second decimal, your standard deviation will be more accurate than someone who only took this to the first decimal. And that would be much more accurate than someone who only went to the nearest whole number. So let's go to the second decimal. Well, realize it's not going to be that terrible. Doesn't matter how big or small the numbers are, it's just making sure we keep track of everything. And again, just by making a little column chart. So those were all my x's. I mean, there's nothing wrong at all with making rows instead of columns. People would say, well, this is x, so let me just go right below here, and I could do x minus x bar right here. That's fine. I don't know, for me, I prefer that they're in columns instead of rows, but some people, a lot of times data is given that way, so it's just a nice, quickie, easy way to follow. But the big difference I'm going to do in this one, I'm not going to bother putting them in order. I'm just going to leave them the way they are. I'm not looking at the mean, the median. We'll just leave that alone. And this time, again, we already saw that summation, so maybe you want to put that down here. Some people like the summation symbol, even if they don't write sum x. That summation, well, it's under the x column, so it should be clear that that is the summation of x. Just tiny little shorthand that some people use. But now, the x minus x bar, and this is what I was just saying a moment ago. Nothing wrong at all doing all of this and then coming to this last instead of going from here to here. So 15 minus 29.33. And just continue. I like to keep that number written here, so just so I can keep coming back to it. It's easy, again, when you're typing in a lot, to just little mistakes. Now they're out of order, so I went from a negative to a positive. You know, I'm all over the place because I never put these in any numerical order, but that's fine. Notice this time, well, I mean, one quick thing, 4 values are below the average, 2 are above. It's not always a perfect split. But again, when you add the deviations, this one, because we rounded, may not be exactly 0. Let's see. We might get lucky. Oops. See, we didn't get 0. We got 0.02. Just a tiny, tiny little bit because these 2 rounded up, whereas these 4 technically rounded down. So it's just that tiny little bit what makes that difference. But now, didn't need to do that. But just to point out, some people, again, they like that little confirmation. And to see 0.02, no big deal at all. That's so close to 0. Knowing we rounded here should make us feel perfectly comfortable. That's not a perfect 0 here, but ultimately this is what we're after. And what I was saying before, I'm not even going to bother with the negative. I know everything's going to be positive here, so I could just get right to it. 4 decimal places, copy them all. Last one. And now we add these. Here's my summation. Again, that's what we're going for. Remember, everybody, formulas, you don't have to memorize them. It's nice if you have them written in a good, convenient spot. You know, if you can just jot the page number where they are, but to have them so that you could always refer to them, the more familiar you are with them, again, the less issue things come up. It's easy to sit back and watch me do all this, but if you don't do it yourself, again, the little mistakes that creep up, even in a take-home exam. So now I've got it. I mean, honestly, some people with their graphing calculator, they kind of skip the column because they're doing the work. They just, everything I entered here, instead of just keeping enter, just put the pluses in between. But again, I've already done it. Just pointing out the tiny little options. All these different options that I'm showing you, you're still showing me work, and that's what I want to see. Again, quite a mess there, but I still want to do quick confirmation. So easy to make those little mistakes. Everything looks good. And we wrap this one up. the standard deviation divided by n minus 1, which in this case is 5, and then take the square root. That would be your variance, because, right, once we take the square root, 22, rounding off now, we'll go 22.5 minutes. I should have kept that in here with the mean, although that wasn't a part of what I was looking for. I needed the value. Ultimately, that was the question, so that one definitely needed the units, but still, good habit to keep the units here as well. So, 22.5 minutes for the standard deviation for this particular set. And again, the little things here, now that you've got the standard deviation, square this value, you get the variance. That's why I pointed out, if you forget the square root, that's where you are. You're not looking at s, because s is the square root. Forgetting the square root, you're looking at s squared. So just that quick little step, just forgetting that square root, people have an answer that sometimes looks crazy, but you're just looking at the variance, you just forgot the square root, and you have the standard deviation. So, let's finish this up. In the very end, they do mention this idea of the interquartile range. I'm going to bring up the quartiles in 4.3. They're a huge part of box plots. But very quickly, it's just a different way at looking at spread. The standard deviation still is a little susceptible to outliers. Certainly not as susceptible to like a range. Oh, and by the way, just to quickly compare, you know, here we were looking at time spent on the phone. Here we were looking at jumps. But now let's just pretend these were also jumps. These people would have jumped in a very similar average to these people, but this standard deviation is much bigger than this standard deviation. Just, again, purely looking at numbers, pretending that these are jumps measured in inches. And again, we're confirming everything we said at the beginning. Similar averages, not everything has to be a similar average, but when you see similar averages or identical averages, to have the standard deviation to tell you a little bit more. Here, both this standard deviation is, you know, that's not tiny, that's still a fairly sizable number, and these data values are fairly spread out, but not as spread out as these. Even going back, looking at the range, lowest value here is 16, highest is 51, so that's a 35 range. Here, the lowest is 9, the highest is 71. That would be a 62 range. So the range is bigger here, the standard deviation is bigger here, there's a bigger spread of your data here. So, it's a good way to measure the spread. Again, the idea of how consistent is the data close together, is it very spread out apart? This tries to give us that measure. So the quartile range, the interquartile range, is a little less susceptible, and that's what you actually use to define an outlier. And the quartile, again, I'm going to define all of this in 4.3. We'll start from scratch with all of this work. It's just about, it's like a lot of median work. The median divides the data in half, but then we have an upper half and a lower half. Let's find the medians of each of those, and those values, you could use those to get another sense of spread, how far values are apart. So I'll talk a little bit more about that. I'm not worried about the interquartile range. I want you to have heard of it. We'll talk formally about how that gives you a formal definition of an outlier, but I'm just going to need you to find the quartiles. So that's 4.3. We'll get to all that. To finish this video, I just want to talk a little bit about how you use the standard deviation in conjunction with the mean. And what we will see, and this will come up in 4.4, why this is the case, but what we like to do, the range of data, the range, actually we already used the words formally, so the spread of data. If you do the mean minus 2 standard deviations, and then separately do the mean plus 2 standard deviations. Notation-wise, if we're in sample, that would be x bar minus 2s to x bar plus 2s. If we're in population, x bar minus 2 sigma, I'm sorry, mu minus 2 sigma to mu plus 2 sigma. This gives us most data values. Most data values fall in between these two values. So, how do we use that? Well, again, let's just hit a couple of the examples we've already seen, and then we'll just slightly expand it. If we go to the test example, if I told you two classes both had an average test score of 75, but the standard deviation for the first class was a 3, the standard deviation for the second class is a 10. Well, that means the first class, most students. What do I mean by most? Well, again, we're going to clarify that more, but it's always a lot more than the majority. We'll start seeing that's going to be at least 75% of your data values. At least. Sometimes it's more like 95%. So most, that whatever definition of most you use, 75%, 95%, that'll always be most. Most of the students with a standard deviation of 3 subtract the standard deviation twice. 75 minus 3 is 72. 72 minus 3 the second time gives me a 69. Add the standard deviation twice. 75 plus 3 is 81. Add 3 one more time, you get 84. That's what happened to most of this class. So the mean is nice, but by having the standard deviation, you're seeing this class is fairly consistent. Not as consistent as we mentioned earlier, where everybody had like a 76, a 74, but still fairly close together. Versus the second class, now subtract 10 twice, same average, subtract 10 twice, and you get a 55, add 10 twice, and you get a 95. This class is way more spread out. Students at the tippy top who are up in the A's, students down in the F's, and all throughout the middle. This class, most students, couple in the top of the D's, but most of your students are all in the 70s into the low 80s, C's to low B's. Here you cover the whole spectrum. This class goes all the way from F to A. So, this was for, again, just looking at class grades. So a lot of students, they want to know, well, how did the class do on this test? What's the average? Average is nice, but then to get a sense of where everybody else is, not just where you stand to the average, that helps you. So you realize, oh, I got a 78. Hey, I'm above average. Well, in this class, you're above average, pretty close to the top of the class, in the better range. In this class, that's 78. Well, you definitely have a lot of students who are a good bit above you here. So just to compare, a different situation. Let's think about like savings. You know, we see a lot of politics going on, and somebody announces a new savings plan. With this new insurance thing, people will save an average of $500 per year. Sounds nice, but who's saving the money? Is everybody saving $500? Are some people saving lots of money and some people saving no money? Goes back to what we said in the beginning. Does everybody save $500? Do half the people save $1,000 and half the people save no money? The standard deviation would help that. That's how we would understand to get that next piece of information. So again, let's just say that average is $500, that average savings. And if I tell you the standard deviation is $50, well, now we're talking about everybody is pretty much saving money. Most people, 2 standard deviations below. 2 standard deviations, subtract 51, subtract it again. You get $400. Add the standard deviation twice. You get $600. And okay, everybody's saving money. Some people are saving more than others, but everybody's saving a decent amount of money with the average being 500. But if that standard deviation was $300, Well, first let me add the standard deviation twice. You'd get $1,100. If you subtract the standard deviation twice, you'd literally get -100. Now, that could be interpreted. If we're talking about saving money, negative savings might mean that your expenses go up. So that could actually make sense here. But look at the difference. Both of these situations are describing an average of 500, but a bigger standard deviation leads to a bigger spread. And now, unlike here where most people are saving money, just some people saving more than others, but pretty much everybody's saving money, now some people saving a lot of money, other people, not only are they not saving money, they're actually spending more. So that second piece of information and that second piece that we want. The mean tells us a lot, but the standard deviation also tells us a lot. That's what we've got. And now, like I said, 4.3, we'll start talking about quartiles. We get another display called the box plot. 4.4, we'll come back to this with what we call Chebyshev and the empirical rule. And these will expand a little bit more about where I'm getting these, why this is a good frame of reference. It's not set in stone. If you go 3 standard deviations above and below, again, it's all little ways, even just going 1 above and below, but by going 2, you always get most of the data. That's why it's just, a good little general guideline to follow. There's nothing, formal about this right here, just trying to get a better sense how the standard deviation works in conjunction